Hello students, today's our topic of discussion is Paschen back effect. In the last topic we discussed about the anomalous Zeeman effect, in which we find out that the spin magnetic momentum interact with the orbital magnetic momentum, and they produces a total magnetic momentum. And when this total magnetic momentum of an atom is placed in a magnetic field H making an angle of theta, this total magnetic momentum will start to rotate about the applied magnetic field. This applied magnetic field in case of anomalous Zeeman effect is very weak, such that it is unable to break the interaction in between L and S. The L and S interaction is large as compared to the individual interaction in between the applied magnetic field and spin magnetic momentum and applied magnetic field with orbital magnetic momentum. But in case of Paschen back effect, the applied magnetic field is so much strong that the interaction in between and LS is small as compared to the interaction in between the individual magnetic fields with the applied magnetic field. In this case, if the magnetic field H is applied, then it is of such strength it makes a strong interaction with the magnetic momentum produced by the spin motion as well as the magnetic momentum produced by the orbital motion. Here the spin and orbit interaction is weak as compared to the interaction between the applied magnetic field and spin magnetic momentum and the orbital magnetic field and the applied magnetic field. Here the energy will change due to the change in the precession of the magnetic momentum due to spin around H and the precession of orbital magnetic momentum around H. In this case, the magnetic field is strong, not very strong, but it is strong enough to break the interaction between L and S. Hence, in case of Paschen back effect, the applied magnetic field is strong as compared to the applied magnetic field in case of anomalous Zeeman effect. In this case, the change in magnetic field is due to the interaction in between these two magnetic fields, one which is applied magnetic field and another the magnetic field produced due to the orbital motion of the electron. And we will find out that the contribution of the orbital motion is given by the magnetic field produced by the magnetic momentum produced by the orbital motion of the electron, its projection on magnetic field, and the strength of the magnetic field. Similarly, there is another term which is contributing in the change of the state of atom by some amount of energy is the spin motion. Due to spin motion, a magnetic field is produced, and that magnetic field will interact with the applied magnetic field, and it will depend the interaction in between, the angle in between them. And let us consider the angle in between them, in this case is theta dash. Then there is the projection of the spin magnetic momentum on the applied magnetic field. We very well know that in vector atomic model we already considered that there are two motion of electron, one is orbital motion and another is spin motion, and due to spin motion a mechanical momentum Ps is produced and a magnetic momentum µs is produced. And we very well know that the relation in between them is µs that magnetic momentum due to spin to the angular momentum due to spin is 2e divided by 2m naught, where ps in terms of quantum mechanics is given by s star h cross, where s star depends upon our spin quantum number having two values plus half and minus half, and total spin quantum number depends upon the total number of electrons. By using all these data, we can easily find out that mu s is equal to 2e divided by 2m naught times of our spin angular momentum, where spin angular momentum is given in terms of our quantum number, spin quantum number, and our Planck's constant, where h cross is given by h upon 2 pi, and we will have 2 times of EH divided by 4 pi m naught times of S star. It is the magnetic momentum produced by the spin motion. Similarly, we can calculate the magnetic momentum produced by our orbital motion, as you know that the ratio of magnetic momentum to the angular momentum in case of orbital motion is given by E times divided by 2m naught, and PL, that is our angular momentum due to the orbital motion, is given by L star h cross, and L star in terms of orbital quantum number is given by under root of L into L plus 1. Substituting this value in the above relation, you will have mu L, that is our orbital magnetic momentum, is equal to E h divided by 4 pi m naught times of L star. And with the help of the orbital magnetic momentum and the spin magnetic momentum, we can find out the change in the energy state of our atom. Hence, substituting the value of mu L and mu S in this relation, you will have change in energy is equal to EH upon 4 pi m naught into L star, and the angle in between the angular orbital angular momentum and the magnetic field, and that is given by L star H with H times, that is the applied magnetic field strength, plus the second term is, it is the contribution due to the spin motion, and it is given by EH upon 4 pi m naught twice with S star, and the cosine of the angle in between the orbit spin magnetic momentum and the magnetic field with applied magnetic field strength. And on solving all these terms, you will have EH upon 4 pi m naught into H constant, and in the bracket you have first term cos of L star H plus 2 times of S star cos of S star H. And very well you know that the L, this term is nothing, it is your magnetic momentum, orbital magnetic momentum quantum number, if H is the applied magnetic field and L star is representing your orbital angular momentum, and if theta is the angle in between them, where we are representing theta like this, then this projection, this horizontal component is given by ml, and this is nothing another than L star cos of theta. It means this whole term can be represented with the help of ml. And similarly, if S is representing your spin angular momentum, and if theta dash is the angle in between the applied magnetic field and the spin angular momentum, then this is the projection, and this projection is your spin magnetic quantum number, and this is nothing another than, that is S star cos of theta dash, and this is your theta dash, the angle between S star and H. To make our calculation easy, or to make our derivation or equation simplify, we are taking EH upon 4 pi m naught times of H, and this is ml plus 2 times of ms. There is a change in energy when there is a change in ml and change in ms. According to our rule, change in our orbital magnetic quantum number may be 0, may be plus 1, may be minus 1. But if a electron is moving in clockwise direction, it will move in clockwise direction when it moves from excited state to the ground state, or from one state to another state. The direction will not change. It will be in clockwise whether it will is in excited state or in ground state, and if it is moving in anticlockwise direction in excited state and now it is moving in the ground state, it will move in anticlockwise direction. It means this whole term will depends upon the change of ml, because there is no change in the value of ms. The direction orientation of the more spin does not change when the electron changes its energy by this factor delta E. For example, let us consider the electron is moving from 2p 1 by 2 to 2s 1 by 2. Now, in our calculations, we have to find the value of ml and ms, where the value of ml varies from plus L to minus L if including 0 and all the integers. Similarly, the value of ms is from plus half to minus half, or plus s to minus s if it is an half integral multiple. It will not include 0. If the value of s is an integer, it will include all the integers between plus s to minus s including 0. In our case, we first find out the value of L and S. In first case, for P, we know that value of L is equal to 1, and from our calculations, we have the value of S is equal to 1 by 2. Similarly, in this case, the value of L is equal to 0 and the value of S is equal to 1 by 2. Next, for our equation, we have to find the value of ml and value of ms. For the given value L is equal to 1, ml have three values 1, 0, minus 1. And similarly, for S is equal to half, ms have two values half and minus half. Let put ms is equal to half for the values of ml, and next we are putting ms is equal to minus half for all the values of ml. Then we have ms is equal to minus half. Similarly, we can find out for the case for the second energy state, and in this case ml is equal to 0, but the value of ms is equal to plus half and minus half. For L is equal to 0, once we will take 1 by 2, and for another L is equal to 0, we will have ms is equal to minus 1 by 2. We have to consider all the positive spins and all the negative spins for all the possible values of ml. Now we have to calculate the value of ml plus 2 times of ms. If we put value of ml is equal to 1 and ms is equal to 2, half in this case, you will have ml plus 2 ms is equal to 2. For the second case, you will get 1. For the third case, you will get 0. For the fourth case, again, you will get 0. It means both these states are same. For both ml plus 2 ms is equal to 0, it means the energy is not changing. It means we both states can be represented by a single line. Similarly, for ml is equal to 0 and ms is equal to minus half, you will have ml plus 2 ms is equal to minus 1, and for the last condition you will get minus 2. For the second state, that is S1 by 2, we will have this value is equal to 1 and this value is equal to minus 1. We can explain this with the help of an energy level diagram with the help of spectral line representation. For 2p1 by 2, if no magnetic field is applied, this energy term can be represented by a single spectral line when no magnetic field is applied. It means magnetic field applied is equal to 0. When a strong magnetic field is applied, then you will get 1, 2, 3, 4, 5 states for this single spectral line. And in these 5 states, these 2 states are not changing energy. It means these 2 states can be represented in the same energy state as your original energy. For ml plus 2ms is equal to 2, you will get an energy state here, and there is a change in energy here. There is no change in energy for both these two values. There is decrease in energy for the fourth value, and there is a decrease in energy for the fourth value. If the electron is lying here in these 5 energy states, and during de-excitation, we find that in the presence of strong magnetic field, this single energy term is divided into 2, having ml plus 2ms value 1 and minus 1. According to our selection rule, ml plus 2ms should be equal to 0 or may be increased by 1 or may be decreased by 1. For these 3 conditions, we will find out how many types of spectral line we can have in our case. If the electron moves from 2 to 1, it means we are changing the state from final state is our 1 and initial state is our 2. It means the change in the value of ml plus 2ms is equal to minus 1, and this is according to the rule. If we jump from 0 to minus 1, then again the final term is minus 1 and the initial term is 0. Again, according to the selection rule, we have the value of ml plus 2ms. It means these are the 2 spectral lines which we will find out for ml plus 2ms change is equal to minus 1. For change is equal to 0, we can move the electron from 1 to 1 and from minus 1 to minus 1. For both these 2 states, the change 1 to 1, that is 1 minus 1 is equal to 0, and minus 1 minus minus 1 is again equal to 0. It means this is according to our selection rule. Similarly, if we move from minus 1, if we move from plus 2 to 1, you will get, let's move from 2 to plus 1. Our final state is 1 and our initial state is 2. We have minus 1, and that is according to our selection rule. Similarly, if we move from 0 to, if we move from 0 to 1, then we will have change in the state is plus 1, as the final state is 1 and the initial state is 0, then the resultant is equal to 1. Hence we get three different types of 6 lines. It means we are getting 3 pair of lines where one line is representing the, for the selection rule, minus 1, one pair is indicating for 0, and another one pair is indicating the value for plus 1. Then this is from minus 1, this is from minus 2 to 1, because for final state 1 and for initial state minus 2, you will have the resultant equal to plus 1, because your final state is minus 1 and your initial state is minus 2, you will get 1. It means you have 6 different lines, and these 6 different lines are exist in the pair, and we get obtained 3 pair of lines with same frequency. Hence, in Paschen-Beck effect, we find out that LS interaction is weak as compared to the interaction in between LH and SH. This happens in case of Paschen-Beck effect. In case of anomalous Zeeman effect, we find out that the applied magnetic field is weak, and due to that LS coupling is strong, and the coupling or the interaction in between LH and SH is weak. And in case of normal Zeeman effect, we only consider the orbital motion and we are not considering the spin motion. In our whole discussion, we find out that atom behaves as a magnet, and this magnet is produced due to the interaction in between the two magnets. One is produced by the orbital motion of the electron and another is produced by the spin motion of the electron. Due to the coupling of these two magnets, we will get the magnetic momentum of our atom, and when this atom is placed inside any magnetic field, the strength of this magnetic field will gives us the different types of spectras, whether it is Paschen-Beck effect, whether it is anomalous Zeeman effect, or whether it is our normal Zeeman effect. It means the magnetic effect in the atom is produced by the two motions, that is our orbital motion and the spin motion. This magnet which is produced inside the atom, or which the magnet, the atom can be represented by this magnet. This magnet is quantized in direction as well as in magnitude, and the quantized direction is given. With the help of mj, we can find out the direction as well as the magnitude of the magnet produced by the motion of the electron in an atom.